The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, let's get started. So here, as I said, I assume that everybody of you has already done the reading. Okay, but what I'm going to do today is I'm not going to repeat any of the things you have already read, but I also don't assume you are already master of the material either. So what I'm going to do is kind of want to give you a view of more or less the same material, maybe a little bit more, but from a slightly different angle. And which means you are going to be seeing the same thing, but like it may look like different. The syntax may be different, and maybe denote things with a different symbol. But like it is essentially the same, and you should be able to reconcile what you read with what I'm going to be writing. And in addition to that, I'm going to ask you to work out some problems by yourself, actually in teams, based on what you read and what I'm going to be describing today. So I brought this thing. I'm going to be asking Alex to take them onto the blackboard later on. And I've also brought markers. So each of you are going to be working with groups of like 2 or 3 to work on problems. Okay, and you're going to see this is the most accurate scheme possible. Okay, to start this, I'm going to be I'm going to be briefly review what you read, which is how to discretize the function. And in addition to writing down formulas, I'm going to be demonstrating things in MATLAB. Okay, discretize a function. Let's start with a function that like most of you very commonly see that in ODEs. When you write down f, let me change to a different color. Okay, if you write down f of t equal to e to the minus lambda t. Okay, can somebody tell me why this function is common in ODEs? It's a solution to essentially the simplest ODE you can find in the world. df dt equal to what? Minus lambda times f of t, right? So if I solve this ordinary differential equation, I'm going to get this function. Okay, if I draw this function, as a function of time, okay, at t equal to 0, the function has a value of 1, right? This is f of t, this is t. And how does the function look like for positive lambda? It's going to decay exponentially. That is what we call exponential decay to the minus lambda t, right? Okay, this function is a function. It is a continuous function, which means it is, in some sense, infinite dimensional. You need infinitely many numbers or infinitely much memory to memorize this function in a computer, right? Because for every t, every single t, you have a function value, f of t. But computers have finite memory, right? Although we have a lot of memory, but still finite. So we need to find a way to represent this function using a finite number of bits in computer. How do we do that? Okay, we do that by first selecting a range. We cannot discretize the function for infinite t. We have to select a range, and let's say from 0 to some big T. Is that enough? No, we also need to discretize this interval into small time steps. And the first time step is usually just 0. The second time step is delta t. and 2 delta t, 3 delta t, 4 delta t, etc. And at t is the last time step. All right. So this discretization, when I do this thing in MATLAB, let me actually start up MATLAB. And when I do it in MATLAB, it is usually how we actually plot a function in MATLAB, right? I believe a lot of you have done this before in some other classes. Here, I'm just trying to warm you up and get you, if you're not familiar, get you familiar again with how do we do things in computer. I think I started MATLAB. Okay, right. So let me set a big T equal to 5. You see this? Is it big enough? Should I change it to a little bit bigger? Anybody wants it bigger? No? Okay. Good. Okay. What delta T do you want? 0.1? Good. Okay. And what I want, how I discretize the time is t equals 0 dt t. All right. This is going to give me a t 1 by 51 double. So if I click on it, it is going to show that the first one is 0, the second one is 0.1, etc., and the last one should be, is 5. All right. And now the function value f of t is equal to, let me set a lambda of equal to 1. Okay, lambda equal to 1. And my function value is equal to exponential of minus lambda times t. So that way I compute a discretized version of this function, f. How do I show the function? I can go to plot and do this plot, but like here I'm just going to use the command line version, plot t and f. Yeah, this gives us exactly the function we expect, right? Exponential decaying function. And I would actually also prefer to plot this and look at what kind of discretization it is. So if I plot this function with a dash and a O, it is going to display a circle at every discretized point. So that we are going to see that this function is actually a discretized function. It is not a continuous. In MATLAB, the plot is approximated by drawing a linear line, drawing a line between two circles. But because delta t is small, it's 0.1, it looks like a smooth function. All right. Okay. Let's try another one. So here, let's see, how do I insert another page option? Insert, after insert. Okay. So let's try another function. We did df dt equal to minus lambda u. How about minus lambda f? How about minus ft squared? Anybody knows how to solve this ODE analytically? Anybody who reviewed ODE before this class when you are reading the readings? Separation of variables? Good. We are going to be dividing f squared on each side, right? So we have df over this f squared equal to minus dt, right? We are going to be integrating both sides, and on this side we get minus f1 over f plus an arbitrary constant equal to minus t, right? So we are going to get f of t is going to be equal to 1 over, we have t plus t, here is actually plus t, right? Agree? Okay, in particular, if I set the same initial condition, which is f of 0 equal to 1, then it determines my constant c, and my f of t is equal to 1 over what? 1 over t, right? Okay, so let's test this function. And it is going to be useful later on, right? So my f2 is going to be 1 over t. Okay, I'm going to be, let me hold on. and plot t f2. Sorry? Oh, okay. +1, right? I'm gonna have a serious trouble if I do this. So let me do this again. Equal to 1 divided by t plus 1. Yeah, thank you for paying attention. Okay. And plot t f2. Let me do dash dash and s. So dash dash means it's a dashed line, and s means squares. So we are going to see how different these are going to be. So one function is the solution of df dt equal to minus f. The other is df dt equal to minus f squared, right? Okay, so here is a discretization of functions, but like this is nothing new, right? We all know this. What's new is how do we approximate the derivatives of these functions? Because if we can approximate the derivative of these functions, then we can start to solve these ODEs numerically, right? These two ODEs I just showed you have exact solutions. But the reason we take this class is because we want to solve ODEs that do not have analytical solutions, right? If we have a way to approximate the derivative of any function we want, then I'm going to show you that we can solve any differential equation we want. Okay, so approximated derivative, not from an analytical function, but from a function discretized, like what we just had, right? So pretend we have MATLAB, we have this f, we have f2, but we don't know where they are computed from. They are just some kind of a discretized function. Now, how do we compute their derivatives? Okay, any ideas? Any ideas? Any ideas? Any ideas? Use the limit definition of derivative. What is the limit definition of derivative? Definition of derivative. 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 f2 minus f1 over f1, 1 over f1, 1 over f1. There is a delta. Okay, you did like half of this. Anybody wants to complete? What's the name? Wants to complete? What's the name? Wants to complete? Okay, anybody wants to complete his answer by maybe changing something, 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 changing something. So is f of t plus delta t minus f of t divided by delta t, right? And this is, of course, the definition of the exact derivative. But in a computer, we cannot take delta t goes to 0, right? That would again require infinite memory and infinite computation time. We have to approximate it. We have to be satisfied with delta t being small enough. Okay, so here we have a function like this. We have a function like this. Each, let's look at this one, the one with squares. Each two squares is spaced over delta t in the horizontal side. On the vertical side, they are spaced by f2 minus f1, right? So if we take the vertical distance divided by the horizontal distance, that's an approximation of this, right? F of t plus delta t minus f of t over delta t. All right? So that's a good way of approximating the derivative. Now, anybody who can transform this formula into MATLAB. I have two functions, f and f2 in MATLAB. How do you guys transform this formula? This is like one of the most important skills you are going to learn in this class. That is how to interpret, how to translate a mathematical formula you can write down on a piece of paper into a code like MATLAB. Taylor series expansion, is that going to give me a code I can type into MATLAB? Like here, I'm ready to type. Please tell me what 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 to type. Please tell me. Yeah, find the function, the difference between functions between one point and other point. Point at other point. Point at other point. Point at other point. Point at other point. Point at. Let me do dark diff. Yeah, difference and approximate derivative. Okay. Okay, you guys are good. So I'm gonna do something new. I'm gonna use diff. I'm gonna use diff of f. What is that gonna give me? So let me just say df equal to diff f. Okay, and let me double click on df to show me what this is. And I'm gonna compare this with f and df. So what I can see is that df gives me this minus this, right? Gives the first element of df is the second element of f minus the first element. Sorry, this minus this. Or what I can do is the same thing can be computed by f of 2 to n. Do you know what this gives me? Exactly. It gives me all the elements from the second to the end. Minus f1 to n minus 1. What does this give me? The first to the second last. So this gives me exactly the same answer, right? And of course, I can just do this divided by dt. All right. And so this is df dt. This is an approximation of the derivative. Okay. And this is an approximation of the derivative at which points if I stick to this formula, to this formula, to this formula, to this formula, to this formula. And the discrete time instances, but like from so if I look at length of df dt, yes, this is an approximation to the derivative from 0 to t minus delta t, right? Because here I'm taking the difference between t plus delta t, which goes all the way to big T, minus ft, which actually doesn't go all the way to big T, right? So I have the derivative from 0 all the way to big T minus delta t. I don't have the derivative of the last one, because at the last one I do not have f of t plus delta t. All right. Okay. Now let me plot. Let me make another figure. I'm going to plot t1 to n minus 1 because I don't have the derivative at the very end and df dt. All right. I'm going to plot them using circles. And is this the derivative? Yeah, this is the derivative. It goes all the way to close to minus 1 to 0. And you can see it is roughly an approximation of the slope of the circle line, right? The slope is negative, therefore the derivative is negative. Let's compare this against the real derivative. Now, what is the real derivative of this function? 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 The real derivative of this function, if f of t is equal to minus e to the minus t, df dt is just equal to negative of e to the minus t, right? Okay, so let's take this figure 2 and hold on and plot t exponential of minus t negative Let's plot it using black. K is black. Okay, we see we had a pretty good approximation of the real derivative. We can also see that it is not exact, right? So if the black line goes right through the center of the circle, then I have a very good approximation. But like we can see, this is it a little bit. All right. So we can see we do have some approximation error, which in this case we call truncation error. Okay, so this, how big the truncation error is the real meat of this lecture. Okay, truncation error. And here we start the Taylor series analysis. So Professor Wilcox last lecture said you're going to have so much fun with Taylor series. So I hope you have already started looking at Taylor series, and it is important you guys do look at Taylor series. Because of importance, I use red. Okay, Taylor series analysis. Okay, so we want to know how much approximation error do we have by approximating the limit with this finite delta t. All right. We want to know what is the difference between df dt and our approximation. So this is at some t, and this approximation is t plus delta t minus f of t. All right. Okay, how do I figure out this difference? How should I figure out this difference? That we can compute both, because yeah, we can compute both, and we can plot the difference. We can subtract this line with this line. We're going to get some number like this is probably 0.05 or something like that. Yeah, this is a truncation error, right? But this only works when we do have an analytical solution, right? So is there any way to estimate how big the truncation error is in a more general way? Taylor series, okay, good. Taylor series. What is Taylor series? And we can summarize what Taylor series is in like one sentence. Yeah, an approximation of a function at some point using the values and derivatives of this function at a nearby point, right? Okay, so here, what we have three things. If you look at the formula, we have three things. The derivative at t, the function value at t plus delta t, the function value at t, right? We have 2 points. One point is at t, the other point is t plus delta t. At one point at t, we have a derivative of the value. At another point, we just have the value. We can apply Taylor series in 2 ways. One way is more convenient. The other two is a little bit more convenient, more inconvenient, but still works. The most convenient way is to expand f at t plus delta t using Taylor series. The more inconvenient way is to expand both the derivative and the value at t using Taylor series based on this point. So let's do the convenient way first. And I'm going to show you we're going to get something similar using the slightly more inconvenient way. All right. So the easy way, let me use green to denote the easy way. Okay, so easy. F at t plus delta t. So start of Taylor series. The Taylor series I write as a formula is k goes from 0 to, let me actually equal to infinity, okay, of f to the kth derivative at t divided by k factorial delta t to the kth. Right, this is what Taylor series is. And in this case, we do not want to keep anything above the first derivative. Okay, so I'm just going to be writing that. I'm just going to be keeping two terms. The first term is k equal to 0. What is f to the 0th derivative? It's just f itself, right? This is k equal to 0. What is 0 factorial? 1. What is delta t to the 0th? 1. Okay, so that is the first term. Now let's do k equal to 1. What is the first derivative of k? It's df dt. What is 1 factorial? 1 again. And delta t to the 1th, that is delta t. Anything above that has a delta t to the at least second order, right? At least delta t squared. So I'm going to write all these terms as a big O times big O delta t squared. Have anybody seen this big O notation before, like in this concept? You did, okay. So what this means is that this thing contains, it can contain infinitely many terms, as long as all these terms has a delta t squared or delta t cubed or delta t fourth. Anything has more of these than 12. Okay. Which is true for all the other terms in the Taylor field. Or maybe green is a little bit too doesn't show really well on this. So let me see if I can. Let me change to this. Okay. Yeah, that's better. All right. Okay. So once we do that, what does it change? Page option. Yeah, I actually don't know what to insert anyway. Okay, once we do this, we can plug this back into the truncation error we call tau. Tau is going to be df dt at t minus something divided by delta t, and that something is, first of all, it's a Taylor expansion of ft plus delta t minus f of t, right? And now it's time to cancel the terms. So I'm going to write this as it is, and first of all, try to cancel the terms here. So delta t is still here. This ft cancels with this ft, right? So we have a df dt times delta t plus O delta t squared, okay? And this delta t cancels with this delta t, and which makes this cancel with this. All right. So what the only thing we get is O delta t squared divided by delta t. Now, if O delta t squared contains all the terms that have delta t squared or higher, then if it's divided by delta t, what do you get? Or the delta t exactly. All right. So what we know is that the truncation error, whatever it is order delta t, which means it decreases as delta t. So to kind of to visualize what this means, if I go back to here, so this is about 0.05, right? The difference between the black line and the blue circles, 0.05. This is for delta t of 0.1. If I increase delta t to 0.2, or let me exaggerate. If I increase delta t to 1, what do you think this is going to get? Yeah, much bigger, of course. How much bigger? Of course, 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 how much bigger? Remember, the error is O delta t. Or let me say, if I just make it twice as large, if I make delta t twice as large, 0.2, Now the difference instead of being 0.05, how big is it going to be? How big is it going to be? 0.1, it is going to be O delta t, which means delta t increases by a factor of 2. This area increases by a factor of 2. Let's just try to do this to see if what I said is true. 0.2, okay. I'm going to be repeating what I'm going to be doing. F is equal to, no, I need to do t first. T equal to this. F is equal to this. And the df dt is equal to this. Right? And I'm going to hold on and plot. I'm going to be plotting t from 1 to n minus 1 df dt, and this time I make it red. All right, so O means I still want to plot in circles, R means red. So let's see what I get. Is it clear? Right, the blue is the derivative I get is delta t 0.1. The red is the derivative I got when delta t 0.2. The error, which is the difference between the circles and the black line. The black line is the exact analytical derivative. It is only available if we have an solution, right? And we are interested in the difference between the circles, which is the numerical derivative, and the black line, which is the real derivative. It grew by a factor of 2. Okay, so this is using the easy way, Taylor series analysis. I'm also going to show you briefly the hard way, which is kind of pointless here, but as you are going to see later on when we get to more complex schemes, we have to start using the more difficult way of doing Taylor series. I'm going to rewrite what is the truncation error we are interested in here. F of t plus delta t minus f of t divided by delta t, right? This is at t. Okay, Taylor series, we are going to do it again, but we are going to represent f of t as a Taylor series of k goes from 0 to infinity, f to the kth t plus delta t divided by k factorial. Here should be what? So I'm expanding f of t with a Taylor series that is based on t plus delta t. Here is something to the kth power. And what is this something? Okay, I'm just going to write a box here. F of y is equal to summation of k equal to 0, Taylor series kth power at x, k factorial, what to the kth power? I'm expanding y at x, at x, at x. Y minus x, exactly, right? Previously, we have x being t, y being t plus delta t. Okay? So y minus x is delta t. How about in this case? Negative delta t, exactly. Okay, does this make sense? All right. Yeah, so this is going to be very useful, like making sure you know every different view, every different manipulation of the Taylor series is going to be useful. I'm going to show you another manipulation of the Taylor series. Okay. That is, if I take derivative to both sides of the Taylor series, take derivative with respect to y, what I'm going to get. If I take derivative on the left-hand side, what I'm going to get? df d, let me just say, df dy is equal to summation k equal to 0 to infinity. What is this term taking derivative to y? It's a constant. There is no derivative. So this term doesn't depend on y. Only this term depends on y, right? So what I'm going to get is k f to the kth power still, right, x divided by k factorial. I'm going to have y minus x to the k minus 1 power times another k here. So this is what happens when you try to expand a derivative as a Taylor series. And now, if you expand this term at t plus delta t, you can arrive the same conclusion as we previously arrived, which is our scheme has a truncation error of order delta t. All right, let's take a mini break of like 5 minutes and then come back to our lecture. All right, so hopefully this gives you kind of a small entry into what we are going to be doing with Taylor series. It's not going to be obvious in the beginning, but like this is going to be getting better and better through exercise. Okay, 5 minutes break. Okay, let's get back to class again. I'm sure I lost all of you when I talked about Taylor series of t on t plus delta t. But like, let's not get hand on to this. It just requires you to go back and look at Taylor series a little bit more familiarity. Okay, so here I'm going to say a little bit of why we want to approximate the derivative, and how is that going to give us a way of solve ODEs. Okay, so remember we are approximating the derivative df dt at time equal to t as f of t plus delta t minus f of t, right, over delta t. And that's not an idea I propose. It's proposed by, sorry, I forgot your name again. Ariel, okay. Okay, so yeah, if we stick to this scheme, we can actually start to integrate ODEs. Okay, let's call this 0 equal to T0. So let's actually call each time step has a name. So T1 equal to delta T, T2 equal to 2 delta T, etc. And the function values f of t at t equal to 0, I'm going to call it f0. The function value at f1, I'm going to call it at t1 equal to f1. The function value at t2, I'm going to call it f2. All right. Now let's say I have an ODE and I only have the solution at t0, t1, t2. I want to know what is the solution at the next time step. What is the value of f3? So that is what happens when we solve ODEs, right? We start with the initial condition. We start with f0 that is given. The task is to compute what f1 is. And now, once I computed f1, the task is to compute what f2 is. Once I compute f2, now the task is to compute what f3 is. How do I compute f3? Yeah, how do I compute f3 using previous data points? So here's what is given. I have the ODE, I have df dt equal to a function of f. Let's say I'm going to say minus lambda times f. All right. So here's my simple ODE. I need to integrate, and I can approximate. I have an approximation to the derivative, and I also have f0, f1, f2. How do I compute f3? So this is given, this is given, This is given, this is given, this is given. How do I put them together to compute F3? Right, we have our function value at F2. We also have an estimate of the derivative at F2, which actually involves the unknown. So let me write down. This is important. Let me write down what is the derivative estimate at F2. At T2, sorry. It is equal to F of T plus delta T, which is T3, right? This is T3. Minus F at T2 divided by delta T. This actually involves an unknown in the derivative. And this is df dt by the differential equation is equal to minus lambda times f at what? T2. Now, through this, by plugging both the approximation of the derivative and by basically putting both the approximation of the derivative and the function together, we converted the differential equation into a what equation? Yeah, into a difference equation, into an algebraic equation. We can just compute, right? So let me color this. This is unknown, this is known, and this is known. We can just move all the unknowns to one side. So f of T3 is my F3, is equal to all the known on the other side. F of T2 is F2, minus delta T times lambda times f of T2 is F2. Right? By doing this, I compute F3 out of F2. Now, what do I do when now I have F3? What do I do when I want to compute F4? Same thing, right? It's kind of recursive because my F4 is now equal to F3 minus delta T lambda F3, right? And I just keep going on. The only thing I need is to plug in the derivative approximation here into the differential equation. Okay. Let me do it again using another different scheme. I have to do this all the time. Okay. Different scheme. Okay, another way to approximate the function. I mean, I have been calling the function f, but like because we started by discretizing a function. But like in solving ODEs, it is more a convention to call the solution u. Okay, so from now on, I'm just going to call my function as u of t instead of f of t. This is just a, but like everything else is the same. All right. All right, agreed. We just call it u of t. Okay. U of t, I have du dt equal to minus lambda times u of t. I'm going to devise another scheme of approximating the derivative. I have du dt at a certain time t equal to u at t plus delta t minus u at t minus delta t divided by 2 delta t. Okay, so let's do two things. One is, why is this a valid approximation to the derivative? 2. Now, if this is a valid approximation of the derivative, how do I make this a scheme of solving an ODE? So anybody has an idea to how to answer either of the two questions? Yes? It's the definition of the derivative, but the definition of the derivative involves a limit. Yeah? Good. As to the world's all problems, it can be solved using Taylor series expansion. Okay, it's good. So answer to the first question, why it's a good approximation. Okay, to answer that, again, we use Taylor series. Okay. U at t plus delta t, as usual, we are going to be expanding it using U at t plus du dt at t times delta t plus O delta t squared, right? This is the same thing as we did of the other scheme. The other scheme is forward Euler, right? Remember your reading. And ut minus delta t, how do I expand that? Yes? Good. It's the same thing except for the distance between this t minus delta t and t is minus delta t, right? So in here, the distance between this variable and this variable is delta t. Here, the distance between this variable and this variable is minus delta t. Therefore, all the values and derivative is the same, except for here, I put minus delta t. And O, it should be minus delta t to the cube, but does it matter? No, it's in the big O notations, the constant coefficients in front of the term doesn't matter, right? So minus O delta t squared is the same as O delta t squared. Is the same as 5 times O delta t squared. It's the same as 1,000,000 times O delta t squared. As long as the terms have a delta t squared in front of it, no matter if it's multiplied by 1,000,000 or 1,000,000,000 or 1,000,000,000, it doesn't matter. It's O delta t squared. If it's multiplied by -1, it's still O delta t squared, right? Okay. So now when I plug in both approximation into this formula, t plus delta t minus ut minus delta t over 2 delta t is equal to these two terms cancel out. These two terms, they actually have different signs, so they become twice as big. 2 times delta t du dt plus, I'm just going to write this down. What is this plus? What is the difference between these two O delta t's? Do they cancel out? No. It's still O delta t squared. Why? Exactly, because you don't know what the coefficients are. Maybe one of these O delta t's has 1,000,000 in front of it. The other O delta t has a 0.001 in front of it. So no matter the summation of them or the difference between them, or they are still O delta t. So this is going to be these two cancel out, du dt, this is at t, plus, again, this O delta t squared divided by delta t, it becomes O delta t, right? Okay, so this is still a good approximation because the difference between them is O delta t. And it is actually stronger than O delta t because in this two Taylor series expansion, you can expand more terms. And you are going to find out the coefficient before these O delta t squares, before the delta t squares, still are going to cancel out. So you're going to get O delta t cubes out of this Taylor series expansion. And over here, you can actually prove that it's in the reading. You can prove that this is not only O delta t, but also O delta t squared. Is it confusing? Does this conflict itself by saying that this is both O delta t and O delta t squared? Do I contradict myself? No? Yeah, how is it both? How can this term here be both O delta t and O delta t squared? Again, yeah, I want to somebody else, yeah.
Because O delta t includes all of the O delta t squared and everything higher than that.
Yes, because O delta t actually includes O delta t squared. O delta t means it can contain a delta t term, a delta t squared term, a delta t cube term. But any or all of these terms can have 0 as their coefficient. If I have an O delta t term, and it happens that the coefficient before the delta t term is 0, then it is automatically going to be O delta t squared, right? So I can say that O1 is a superset of O delta t, which is a superset of O delta t squared, which is a superset of O delta t cube, etc. Right? Any questions? Questions? All right. Okay. And so now the second question is how to make a scheme out of it. We already have an approximation, that is du dt at t is equal to u of t plus delta t minus u of t minus delta t divided by 2 delta t. We have a differential equation, du dt equal to minus lambda u. Again, the only thing you need to do is to plug this into this. So we have u of t plus delta t minus u of t minus delta t divided by 2 delta t is equal to minus lambda u at t. And when you look at these terms, when you are at time t, when the solution at time t is already known, but anything beyond t is unknown, then this is known because this is before t. This is known because this is at t. The only unknown is this. So again, we are going to rearrange the terms and say u t plus delta t is equal to u t minus delta t minus 2 delta t times lambda times u2. All right. If t is going to be exactly on the time step, what I'm going to say is that u of I plus 1 is equal to ui minus 1 minus 2 delta t lambda times ui. Okay, this notation is assuming I have discretized u into a uniform grid of spacing delta t. Yeah. The question is, am I using a scheme that has a mathematical definition?
What a scheme means.
Oh, okay. So what does a scheme mean? A scheme is a numerical method, a method that you can implement into the computer to solve a differential equation. It just means if I have an initial condition, a scheme must be able to tell me what is the solution at the next time step, and then tell me again what is the solution at the next time step, etc., etc. Right? A scheme It's basically, you can think of it as an algorithm. Right. Or making what? Exactly. Yeah. Good question. Yeah, I was just so familiar with what scheme is, I didn't explain it, so it's a good catch. Yeah, if you find something like this, please do raise the question, because if you have a question, your classmates probably also have the same question, right? Okay. So here we basically derived two schemes. By the way, this scheme is the midpoint scheme. We have derived two schemes: the forward Euler scheme, which is the scheme that we have. Yeah, the scheme we have here. We can write it in general as f of I plus 1 equal to f of I minus delta t lambda fi. So this is the forward Euler. This is called the forward Euler scheme, and in your reading, okay. And we have also derived the midpoint scheme, both from they are different only by that they are their difference in how to approximate the derivative in time. Right. Once you have an approximation of the derivative in time, you plug into the differential equation, you get a scheme. Okay. Now, what I want to talk about next is what is the local order of accuracy, and I'm going to say that the local order of accuracy is how accurate the scheme approximates the time derivative. It is related to what tau is. So, for example, in forward Euler, tau is O delta t, right? This is what we derived right before we take the break, right? So tau is tau in forward Euler is the df dt at t minus let me call it u, because it's more consistent to the notes. Minus u at t plus delta t minus ut divided by delta t. This is O delta t, okay, for forward Euler. And the tau is the same derivative minus a different approximation for the derivative ut minus delta t divided by 2 delta t. This is actually O delta t square for the midpoint, and through Taylor series analysis. Okay, the local order of accuracy is the exponent on top of delta t of this truncation error. So forward Euler is first order accurate because it's O delta t. Midpoint is second order accurate because it is O delta t squared. So the local order of accuracy is 1 for forward Euler. The local order of accuracy is 2 for midpoint. Usually, the higher the order is, the better scheme is. Why? Because you can make the scheme more accurate by only increasing or decreasing delta t a little bit, right? We just did analysis of forward Euler. If I make delta t half as small, how much smaller the truncation error is going to be? Half. Now, if I have a midpoint, if I decrease the delta t by half, how much more accurate is the midpoint going to be? A quarter, exactly. So, yeah. So this is how we usually kind of visualize the order of accuracy. Okay, so let's say the x-axis is delta t. Okay, so let's say this is forward order. Yeah, so let's say this is a first order accurate. This is delta t, and delta t, let's say, is 1 here, 0.1 here, 0.01 here, 0.001 here. Okay, so let's say when you have 1, I get a pretty big error, let's say here. When I decrease delta t to 0.1, what do you think the error is going to become? The 10th, right? So I should be right here, right? I should be right here because it's O delta t. Now, if I decrease it to 0.01, it should decrease by another 10 and by another 10. So if I link it, it'll be a line with a slope of 1 in a log-log plot. All right. Now, so this is forward order. This is first order accurate. How about a second order accurate scheme? So again, if I delta t is 1, 0.1, 0.01, 0.001 here, and again, if I'm pretty large error at delta t equal to 1, what do you think is the error going to be at delta t equal to 0.1? Where? Top of my head. Down. Why it should be here? It's delta t square. When I make delta t 10 times smaller, delta t square is 100 times smaller. So I should be here when delta t decreased by a factor of 10. I should be here when delta t is decreased by another factor of 10. If I link it, it'll be a slope like this, and I'm kind of out of chart when I'm 0.001. So you can see that second order scheme is going to be much better than the first order scheme, right? Especially if I have the luxury of making delta t very small. Okay, so going back to MATLAB, if I can say df dt equal to, now I cannot no longer do diff, right? I have to do f of 3 to n. What does 3 to n mean? Yeah, let me make it. Let me clear the workspace so that you can see better. Clear command window. Yeah. Okay. So df dt. Let me say midpoint is equal to f of 3 to n minus f of 1 to n minus 2. What does this mean? I'm taking from the third value to the last value, minus the first value to the third last value. Okay. I'm taking the difference space by 2. Okay, so that is how I do f at t plus delta t minus f of t minus delta t. So I should divide this by how much? 2 times delta t, exactly. And here I think I'm actually doing a pretty big delta t. It doesn't matter. Okay, so when I plot it, I should be plotting it against the t going from 2 to n minus 1, right? Because this is now my t. Okay, 2 to n minus 1 is my t. 3 to n is my t plus delta t. 1 to n minus 2 is my t minus delta t. So this is my t. I'm going to plot this against the f dt midpoint. I'm going to be square, and what color do you want? Pink? Magenta, okay. SM? S is square, okay. Yes. So see, even though my delta t is 0.2, I'm getting kind of goes right through the exact derivative. Okay, so this is how a second order scheme is better than a first order scheme. And how to assess that? Taylor series analysis, right? Okay. Maybe I'll just show you how I get the second order. So if I further expand this, here what I get is the d square u dt times delta t square over 2, right? Again, square over 2, and then plus the cube. Here what I get is plus d square u dt times minus delta t square, which is the same as delta t square over 2, plus this to the cube. And you can see when I subtract the u of t plus delta t by u at t minus delta t, the 0th order term cancel. The first order term, because they are the same, so they add together, and the third order and the second order term also cancel, right? The third order term again is going to have different sign, and subtracting them actually makes them bigger. So it is order 2. So here I can modify this to delta t cube because the square term actually cancel each other, and here is going to be square. All right, and we see that by actually observing the increased accuracy. Okay, so let's we have a little bit of time. Let's actually start the contest, and I would actually not end it today. I would have you start it today, and maybe we'll come back and report your findings in the beginning of the next lecture. All right. So the contest is like this. I want the best X scheme. How do I quantify best? The highest local order of accuracy. Okay, what does that mean? I want to O delta t to the as high power as possible, right? Okay, and the X, what does X mean? X means one of these 4. And I like you to form a team with 1 person or 2 other persons and commit to either 1, 2, or 3, or 4. And figure out how do you design a scheme to make it as accurate as possible. Okay, so I'm just going to I'm going to give you the formula now. Best implicit one-step scheme means I want u at k plus 1. Let me use I. So u at I plus 1. Or let me actually use like u of t plus delta t equal to something times du dt at t plus delta t plus something times u at t plus something times du dt at t. All right, this is the best implicit one-step scheme, and your task is to figure out what the questions are. Okay, best explicit two-step scheme. It means this. It means u at t plus delta t has to equal to, because it is explicit, it do not allow a derivative at t plus delta t. So you have to do a question mark of ut plus a question mark at du dt at t. And now because it's two-step means I allow one more step to be used in determining the solution at t plus delta t, which means I can use u at t minus delta t and du dt at t minus delta t. All right. So this is the degrees of freedom you have in your best explicit two-step scheme. And what is the difference between an explicit two-step scheme and an implicit two-step scheme? Yes, the answer is you can use du dt at t plus delta t. So I'm going to circle the term that makes a scheme implicit, right? So implicit. So with the implicit scheme, you are allowed to use ut plus delta t equal to the implicit term is a question mark times du dt at t plus delta t. If I don't have this term, it'll be explicit. All the other terms are the same, question mark times ut plus question mark times du dt at t plus question mark u at t minus delta t plus question mark times du dt at t minus delta t. So let's just choose between the three, the first three options. Okay, and time is over, but like I like you to find a teammate, commit to one of these axes, and come up with an answer, and we'll start to discuss this in the next lecture.